So by now, you should be starting to have a bit more of an understanding of what all those little elements of a sentence of code mean. Well, that's all well and good, Rex, but how do we turn this code into statistics and supporting visualizations? Well, that's what we're going to be looking at in this tutorial. That's right, we're going over basic plotting and analysis. Welcome to the Skullywag Lab. I'm Dr. Rex. In this set of tutorials, I'm presenting a bare bones introduction to the basic fundamentals of R coding. Just how exactly do we use this code to put together these interesting statistics and plots and visualizations that we see online? Like, what is this sorcery? Well, today I'm going to be showing you some of the most common functions and their arguments to help you understand the process. So let's get into this. Let's bring in some data. The iris dataset is a classic dataset used by many a budding R coder. We can see in the environment that the dataset has 150 measurements of 5 variables. Typing iris into the help box will tell you about the dataset. It's a dataset of sepal and petal measurements from the flowers of 3 species of iris plants. Using the head function on the dataset, we'll print out the first 6 rows of data. This is a tidy little function that just lets you take a quick look at the format of each variable. So we can see 4 quantitative or numerical variables, and the species name is a 5th qualitative or categorical variable. Using the summary function, we'll print out the summary statistics, such as the means, medians, interquartile ranges for each variable. I'll also point out that this data is arranged in a 2D matrix format, and we can therefore isolate specific values of interest using row and column coordinates. For example, the data point positioned on the first row and second column is 3.5. This happens to be the sepal width of the first observation of the dataset. Let's extract some variables from the dataset. Firstly, we'll grab the variable for petal length and allocate that to a new object. This is now saved in the environment. We'll also grab petal width and also species. Let's just quickly look at the species variable, because these kinds of variables are a little different to the numerical ones we're used to. You can see it listed as a factor and has 3 levels representing the species names. Let's do some plotting. There are so many plotting options available that looking at the function doesn't really tell us much in a clear and concise way. So I'm just going to take you through the basics. Firstly, let's just use the plot function on the whole dataset. This plots each variable against another and is a really cool way to do some early exploring of how the different variables relate to each other. We can expand this by clicking on the zoom button at the top of the plot window. You can see from this that some of the variables appear more tightly correlated, others not so much. So let's isolate a nice clear relationship here by plotting petal length with petal width. This just makes a simple plot of the points. But this is so boring. We should try to spruce this up a little bit. Let's first give these points a nicer color. Let's go with red. And a new plot is printed into the plot window, this time with red points. But you know what? I don't really like these open circles very much. I want closed, fully colored points. Let's change the point characters to filled squares. We now have a new plot with red squares for the points. Next, I want a title. Let's add one. Awesome, this plot is really starting to come along now. But you know what? The axes names are a bit ugly. Let's change those too. Nice one. But maybe red isn't enough, because we have 3 species, right? I want to see the distributions of all 3 species. So let's create a temporary list using the concatenate function. Fill it with some colors to represent each species, and then allocate each color to a point using the species factor we created. Now we can see each species. Unless! Maybe you're colorblind. Or maybe the plot is printed in monochrome and you can't tell the difference. Let's do the same thing with the point characters. Now we have different colors and different symbols for each species. Brilliant! But what are these point characters? And what do the numbers mean? Well, this is what they look like. Each number corresponds to a different symbol. So you can see that the default is number 1, which is the open circles. And then later on, we switch that for the closed square with number 15. And after that, we swapped for the temporary list of the closed square, closed circle, and closed triangle at 15, 16, and 17. But something's still missing. We don't know which species is which. That's right, we're missing a legend. The legend function is a simple overlay function, meaning that it overlays new imagery onto the previous plot. Again, there's lots of options here, so I'll just provide the basics. So in this line of code, I have the x and y coordinates of the plot where the top left of the legend will be. The legend command names each group. We have the colors, point characters, CEX refers to the point size, and the last part just means I don't want a box to be drawn around my legend. It stands for border type. And there you have it. Okay, time for some basic linear modeling. We've looked at the LM function a few times in previous tutorials, but we haven't actually used it. So let's do that. We create a new object with the assignment operator and use the LM function with a response variable and a predictor variable separated by a tilde. This object now appears in the environment with a blue arrow indicating that it has a list of outputs within. If we click on the magnifying glass, we can see what these are. Stored in this object, we have all the coefficients, residuals, fitted values, and everything else. We can access any of these with a $ symbol, which kind of translates to within this object. For example, typing the object name followed by the contained vector of coefficients prints out the y-intercept and the slope of the equation. Using the summary function will return the model statistics, including the y-intercept and the slope under the estimate column, t-statistics, p-values, and down the bottom we also have the r-squared values and the f-statistic with degrees of freedom. We can also use these coefficients to generate a trend line for our plot. We do this using the AB line function. According to the function details, in order to produce a simple line across your plot, you simply need an intercept and a slope. And that's what we have. Just like for the legend, AB line is an overlay function which superimposes the new feature onto a pre-existing plot, instead of plotting an entirely new plot. So let's run the AB line function with those coefficients. And now we have a trend line. Alright, next let's do an ANOVA using the species as a predictor variable. So this time we use the LM function just like we did before, but this time we're looking at petal length across the different species. Then we use the ANOVA function, which produces the ANOVA statistics for the model, including the degrees of freedom, f-statistic, and p-value. As you can see, highly significant. Now let's generate a box plot of the 3 species to look at those differences. As for the other plot functions, there's tons of ways to change the plots to suit your preferences, but the simplest box plot only requires the response variable and the predictor variable. So let's do that with petal length and species. Nice one, mate. Alright, next I'm going to show you how to subset your data to test specific groups or observations of interest. Let's say we just want to compare 2 species. Maybe we're interested in comparing Setosa and versicolor. Looking at the vector of petal length values, we can see that Setosa and versicolor occupy the first 100 observations. We use the square brackets to create a subset of the first 100 observations. And you can see we now have a vector of those 100 values saved to the environment. And we can also do the same thing for the species variable. But there's another way to do this that I want to show you as well, because it's a little bit more technical, but in some cases it can be a little bit more efficient. Remember from tutorial 1, when we use the 2 equal signs, we get a vector of logicals printed out. Logicals being true or false. Well, we can do this first to find out which observations belong to the group we're not interested in. Then we use the which function to determine the observation numbers in the data set that belong to this group. That's 101 to 150. But do you also remember from tutorial 1 that we can use the exclamation mark to reverse logicals? So let's do that for the which function. So what this does is return all values that don't belong to the group we're not interested in. In other words, it returns the values of the two groups we are interested in. Now, because this is a vector of numbers, we can sub this into the square brackets to represent the observations we want. And there you have it, the exact same vector. And then we can do the exact same thing for the species factor. Now, if we run another box plot, we should just have these two groups appear in the plot, right? Uh-oh. Why are there still 3 species here? Well, if we look at the levels of the species subset, the values might be subset, but there's still 3 levels there. This means we need to remove unused levels from the factor. We do this using the drop levels function. Now you can see there's only 2 levels. Once we've done that, the box plot should work as we want it to and just show us the 2 species we want to see. Yep, there it is. Like clockwork, baby. And we can also make this one prettier using the same arguments as for the other plots. As a final exercise, let's do a chi-squared test. But first, let's generate a fun little data set. I'm going to create a matrix called Skullywag, but instead of using the matrix function, I'm going to create a table. We use the asTable function, and within this we use the rbind function. Rbind is a function for binding rows together. To create these rows, we use the concatenate function, and within the function parentheses, we type 3 numbers to make up each vector. We run all this together and Bob's your uncle. This generates a table of 2 rows and 3 columns made up of those 6 numbers. Phew. Next, I want to name the rows and columns. We do this using the dim names or dimension names. We make a list. Again, this always follows the ordering of rows, then columns, then layers. Let's call the rows personality with 2 names, legends and losers. Then for the columns, let's call them opinion with 3 options: love skulls, indifferent, and hate skulls. Now this is a good looking table. Now we create a new object and use the chi-squared test function on Skulliwag. This creates a list of all relevant material in the environment. Oh, would you look at that p-value right there? That's pretty significant. Using the $sign with observed prints out the observed values, which is the values from our table. Doing the same for expected prints the expected values for each category. We can already see that there are fewer legends predicted to love skulls and fewer losers predicted to hate skulls. Very interesting. Printing out the residuals shows the directionality of the differences between the observed and expected values. As you can see, more legends definitely love skulls than expected, and more losers definitely hate skulls than expected. This is, of course, not surprising in the slightest.
Don't half-wit! Bunglers!
Alright, we're done. You've made it through another aspect of R coding. The next tutorial is just going to be a short one covering the simplest ways to format your data for importing and also exporting if you need to. If you found this content useful at all, don't forget to like and subscribe, and I will catch you in the next one.